So today we'll start with balancing of uh, reciprocating masses. Let's say we have a piston cylinder arrangement here, as you can see. Uh, the connecting rod length is L. Okay. Angular displacement of crank is at theta. Omega is the angular velocity. Okay. So the different forces acting on it are, let's say, Fi, Fr, okay. Then here Fbh, this is the vertical component of Fb, that is Fbb, and this is here Fb. Now what are they, will elaborately discuss. So we can write the resultant of all the forces acting on the body of the engine due to the inertia forces only is called unbalanced force. Unbalanced force. Now let Fr is the force required to accelerate the reciprocating part. Reciprocating parts. Fi is the inertia force due to reciprocating parts. Fn, the normal force on the cylinder, Fb, the force acting on the crank bearing, Now we'll discuss about the primary and secondary unbalanced forces of reciprocating masses. Okay. So primary and secondary unbalanced forces of reciprocating masses. Right now, let m is the mass of reciprocating part, L is the length of connecting rod, R is the crank radius, theta is the angle of inclination of crank, omega is the angular speed, of crank, n is the ratio of L and R, you can say, okay, L and R, so it is L by R. Now the acceleration of reciprocating mass denoted by A subscript R is equal to omega square R whole into cos theta plus cos 2 theta by n. This we know in dynamics 1. Okay. Now the inertia force due to the reciprocating parts that is Fi is equal to your mass into acceleration. So we can write this as m omega square R cos theta plus cos 2 theta by n. This is the inertia force. Now the unbalanced force we can write so the unbalanced force let's say it is given by Fu is equal to your m omega square R cos theta plus cos 2 theta by n, that is the inertia force. Okay, so it will be equal to m omega square r cos theta plus m omega square r cos 2 theta by n. Okay. So it is basically a primary unbalanced force Fp plus secondary unbalanced force Fs. Okay. So remember this. This is known as your primary unbalanced force, okay, and this one is secondary unbalanced force. So now we will discuss about the partial balancing of unbalanced primary force. Unbalanced primary force. Let us say we have a schematic like this. Omega, this is the unbalanced force M, so there will be centrifugal force M omega square r, angle of inclination of crank is theta, okay. So it has to balance by another mass B, okay, and this angle is also theta. So this component will be B omega square B cos theta, okay, where the distance is B, okay, and the vertical component is capital B omega square B small b sin theta. Okay. Now the primary unbalanced force, we can say primary unbalanced force is m omega square r cos theta, okay. Now centrifugal force due to mass B is B omega square B, okay. The horizontal component of this force opposite to the primary unbalanced force is equal to B omega square B cos theta, okay. So the primary unbalanced force will be balanced if we can say that b omega square b cos theta is equal to m omega square r cos theta. Okay. In other words, we can say when b dot b is equal to m dot r, the primary unbalanced force will be balanced. Okay. This is the criteria. Now consider a fraction c of the reciprocating mass is balanced. Reciprocating mass is balanced. So c times of mr is equal to b dot b. As we are discussing about partial balancing, so it is presumed that some fraction of the total reciprocating mass is balanced. Let us say it is c times. So we multiply here with c in mr. Okay. So c times of m dot r should be equal to b dot b. Now the unbalanced force along the line of stroke is equal to m omega square r cos theta minus b omega square b cos theta. Okay. Or we can say m omega square r cos theta minus c times of m omega square r cos theta by substituting the value of b omega square b cos theta. So in other words, it will be 1 minus c times of m omega square r cos theta. Okay. So now the unbalanced force perpendicular to the line of stroke, okay, will be b omega square b sin theta only, because the m omega square r component will be horizontal. Okay. So in other words, it will be c times of m omega square r sin theta. Okay. So the resultant unbalanced force at any instant, okay, will be equal to 1 minus c m omega square r cos theta, the horizontal component, okay, square, plus c times of m omega square r sin theta square whole root over. Okay. So it will be equal to m omega square r, taking common, will have 1 minus c cos square theta, 1 minus c square cos square theta, plus c square sin square theta. Okay. Now if the balancing mass if the balancing mass is required to balance the revolving mass as well as the reciprocating mass, okay, then your B dot B will be equal to m1 dot r plus c times of mr, okay, or you can say m1 plus c dot m, okay, into r, where we can say m1 is the revolving mass, okay, and m is the reciprocating mass. We will take an example, okay, on this. Let us say the question is given like this: a single cylinder reciprocating engine has a speed of 240 rpm, okay, stroke is 300 mm, okay, mass of reciprocating parts is 50 kg, mass of revolving parts at 150 mm radius is equal to 37 kg, m1 is given, if 2/3 of the reciprocating parts and all the revolving parts are to be balanced find bit 1 balance mass required at a radius of 400 mm, and the residual unbalanced forces okay, when the crank rotation, when the crank rotation is 60 degree from inner dead center IDC. Okay. Now looking into the given data, we have speed n is given 240 rpm, so we'll have the angular velocity omega 2 pi n by 60, so it will be 2 pi into 240 by 60, so that is 25.13 radian per second. Okay. Now stroke is 0.3 meter, okay, because it is given 300 mm. Mass of reciprocating parts is 50 kg. Mass of revolving parts, okay, or revolving mass m1 is 37 kg. Radius, crank radius 0.15 meter. Okay, the value of C, okay, the portion of mass to be balanced, it is 2 by 3, because in the question it is written 2/3 of the reciprocating part, so C value is 2 by 3. Now let capital B is the balance mass required. We need to find this balance mass required. Small b is the radius of rotation of balance mass. That is 0.4 meter, it is given in the question. Okay. Now as per the relation, we have B dot B is m1 plus C times of m into R. Okay, so we'll have B into 0.4 is equal to 37 plus 2 by 3 times of 50 into the crank radius 0.15. So we'll have the balancing mass capital B will be 26.375 kg. We got the balancing mass. Okay. Now next is the residual unbalanced mass. Okay. That will be equal to m omega square r, okay, 1 minus c square cos square theta plus c square sin square theta whole root over. So 50 into 25.14 square into 0.15 root over of 1 minus 2 by 3 square cos square 60 plus 2 by 3 square sin square 60. Okay. So this will be equal to 2848.47 Newton if you calculate. Okay, please cross check it. Okay. this will be 2848.47. Now the next part, how to find out then we will consider partial balancing of locomotives. Partial balancing of locomotives. I think the example is completed because it is given here. Now coming to the partial balancing of locomotives, you can write here as the engines of a locomotive are generally placed at right angle to each other. At right angle to each other to have an uniformity in turning moment diagram. Turning moment diagram. The two cylinder locomotives generally classified as first one is inside cylinder locomotives, okay. Second one is outside cylinder locomotive. Inside cylinder, outside cylinder, okay. Now coming to the schematic for inside cylinder locomotive, let's say we have the driving wheels like this. So let's say this is the first engine. The next engine will be at 90 degree to the first one. Okay, so it is engine 1, it is engine 2. These are the driving wheel. Okay. So for the outside cylinder locomotive, let's say the driving wheels are placed here. So this is the first engine, engine 1. This one is the second engine, that is engine 2. Okay. So here we can write that the engines are placed placed between the planes of two driving wheels in case of inside cylinder locomotives, whereas here you can say the engines are placed outside the driving wheels. So this is the basic difference between inside and outside locomotive. Now a single or also known as uncoupled locomotive is one in which the effort is transmitted to one pair of the wheels only. One pairs of wheels only, whereas in coupled locomotives the driving wheel are connected to the leading and trailing wheel by an outside coupling rod. Okay. Now we'll discuss about the effects of partial balancing of reciprocating parts of two-cylinder locomotives. Now, due to the unbalanced primary forces, primary forces along the line of stroke okay, and perpendicular to the line of stroke the following effects are generally found. Are generally you can say observed. Okay. First, there is a variation of tractive force along line of stroke. Second effect is called swaying couple, SWAYING, swaying couple. Okay, so these are very important. Now the effect of primary unbalanced force now these two effects, remember these two effects are due to the unbalanced primary force, you can say primary force parallel to the line of stroke. Now the effect of primary unbalanced force okay, perpendicular to the line of stroke is known as hammer blow. Okay, it is called hammer blow. Now we will discuss all the effects one by one. So first is variation of tractive force. Which occur generally due to the unbalanced primary force parallel to the line of action. Okay, let's say we have the schematic like this. The cylinder, the line of stroke, we have the connecting rod, then crank. Okay, now this is the angular velocity omega, inclination of the crank with horizontal angle theta, mass of the reciprocating parts. Okay, now the component this component will be m omega square r sin theta, and this component will be 1 minus c times of m omega square r cos theta, as we are discussing about partial balancing. Now if the first crank, you can write here, if the first crank inclination is angle theta, the inclination of second crank will be will be 90 plus theta. Okay. So let can say m is the mass of reciprocating parts per cylinder. Okay, in case of per cylinder. Okay. C is the fraction of reciprocating parts to be balanced Okay. Now the unbalanced force, right, the unbalanced force along line of stroke for cylinder 1 will be equal to 1 minus C m omega square r cos theta. Okay. Similarly, for second cylinder it will be 1 minus C m omega square r cos 90 plus theta. Now the tractive force, as you know, now the tractive force which is denoted by Ft which is equal to the resultant unbalanced force along the line of stroke will be equal to 1 minus C m omega square r cos theta plus 1 minus C m omega square r cos 90 plus theta. So Ft can be denoted by 1 minus C m omega square r, taking common will have cos theta minus sin theta. Okay. Remember the formula for Ft: 1 minus C m omega square r cos theta minus sin theta. Okay. Now this Ft is maximum or minimum when we can say cos theta minus sin theta. Okay, cos theta minus sin theta is maximum or minimum. Okay. Now for cos theta minus sin theta to be maximum or minimum, maximum or minimum. Okay, uh, d by d theta cos theta minus sin theta should be equal to 0. Okay, or we can say minus sin theta minus cos theta is equal to 0. So we can say minus sin theta is equal to cos theta, or we can write this as tan theta is equal to minus 1, or we can say theta is either 135 degree or 315 degree. Okay. Now the maximum or minimum value of attractive force, maximum or minimum value of attractive force plus minus 1 minus c m omega square r cos 135 degree minus sin of 135 degree will be equal to plus minus root 2 1 minus c m omega square r. Okay, this is the value. Similarly, now we will discuss about the second effect, which is known as swaying couple. Swaying couple. Now let's say the unbalance, we can write the unbalanced forces along the line of stroke of the two cylinder constitute a couple, okay, about center yy, so we can say this is a by 2, this one is a by 2. Okay. Total distance is a. So this is 1 minus c m omega square r cos theta, and this one is 1 minus c m omega square r cos 90 plus theta. Okay, so constitute a couple about center yy and tend to vary, we can continue here, tend to vary and sway the engine alternatively alternatively in clockwise and anti-clockwise and anti-clockwise directions. So now let A, you can say, let A is the distance between the center lines of the two cylinders. So the swaying couple is equal to 1 minus C m omega square r cos theta into A by 2 minus 1 minus C m omega square r cos 90 plus theta into A by 2. So the simplification would lead to 1 minus C m omega square r, taking common A by 2 common, we have cos theta plus sin theta. Now for maximum and minimum values, we have d by d theta cos theta plus sin theta is equal to 0, or you can say minus sin theta plus cos theta is equal to 0, or we can say tan theta is equal to 1, or theta can be either 45 degree or 25 degree. So the maximum and minimum values are of swaying couple are plus minus 1 minus C m omega square r A by 2 cos 45 plus sin 45, or we can say plus minus A by root 2 into 1 minus C m omega square r. Okay. Now the last effect is the hammer blow due to the force along perpendicular to the line of stroke, hammer blow. Now the maximum value of unbalanced force, we can write maximum value of unbalanced force along, or we can say perpendicular to the line of stroke stroke is called hammer blow. Okay. So this hammer blow is basically B, the balancing mass omega square into balancing mass radius small b, B omega square B. Okay. So the effect of hammer blow is to cause variation in pressure between the wheel and the rail. So let P is the downward pressure on the rail okay, and the net pressure between wheel and rail is equal to P plus minus B omega square B. Okay, and the net force acting downward will be, this is the net force acting the net force acting downward will be P minus B omega square B. Now if this P minus B omega square B is negative, the wheel will be lifted. From rail. Therefore, the limiting value of P is equal to B omega square B. Okay, the permissible value of angular speed will be angular speed will be omega is equal to P by capital B dot small b. Okay. So in the consequent classes will be solving few examples on this.